Welcome to Prime Numbers Part 3. In this lesson, I'm going to go over a number of a bit more difficult problems compared to the previous lesson, Part 2. For our first problem, we want to show that every prime p not equal to 2 or 5 divides infinitely many numbers of the form shown here, so basically a series of ones. These numbers are called repeated units or just rep units, and they're denoted by R sub n. So we write it like this here. So notice if we put in 1 for n, you get 10 minus 1 is 9, divided by 9, you get 1. If you put in 2, you get 100, minus 1 is 99. You divide that by 9 and you get the second one here, and so on. So we want to show that for any prime p, other than 2 and 5, there are infinitely many integers n, such that R sub n is congruent to 0 mod p. I have two different solutions for our problem. The first one is based on the pigeonhole principle. It's pretty simple in concept. Let's say you had 10 pigeonholes, 10 containers, and you had 11 balls, and you had to put the balls into the containers. Then the pigeonhole principle says that since you have more balls in containers, at least one of the containers is going to have 2 balls in it, right? The best you could do in terms of avoiding multiple balls in the containers would be to put 1 ball in each of the 10 containers, and then you still have one more ball, and that forces you to have at least 2 in one container. So we'll use that idea here. It comes up a lot in combinatorics. So consider first the p plus 1 rep units, R1, remember that's just 1, R2 is 1, 1, up to R sub p plus 1. When we divide any number by p, there are only p possible remainders, 0, 1, 2, p minus 1. That's true whether or not p is a prime. We'll need the fact that p is a prime later, but for now we don't need that. Since we have a list of p plus 1 numbers, by the pigeonhole principle, at least 2 of these numbers must have the same remainder when divided by p. Let these 2 numbers be R sub m and R sub n, where m is bigger than n, and of course m and n are in this list here from 1 to p plus 1. Thus we have that R sub m is congruent to R sub n mod p, or we could write it this way here, R sub m minus R sub n is congruent to 0 mod p. Then the next thing to notice is if you subtract 2 rep units, you get a sequence of 1s followed by 0s. So for example, if we take R5 minus R3, we get 5 1s minus a sequence of 3 1s, and we get 1 1 0 0 0, which is really R5 minus 3 times 10 to the third, or just R2, in other words 11, times 10 to the third. So you notice the 3 and the 3 appear here and here, and then this 5 is this number. So in general, just extending this pattern, if we have R sub m minus R sub n, that's equal to R m minus n, just the way we did 5 minus 3 here, times 10 to the nth power. So p divides, just going back to this here, p divides R sub m minus n times 10 to the nth power. Now here's where we use the fact that p is prime and it doesn't equal 2 or 5. This condition here, you can see now why we put this in place, because if p does not share any factors with 10, in other words 2 or 5, then the GCD of p and 10 is 1. Further, we can't divide p into 10 to the n either, because p is not 2 or 5. So for the product, R sub m minus n times 10 to the nth power to be divisible by p, given this relatively prime aspect here, P must divide R sub m minus n. We'll just let K equal m minus n. So we have found one rep unit, R sub K divisible by P. And since P divides R sub K, it also divides any rep unit whose length is a multiple of K. In other words, it'll divide R sub CK, where C is an integer. That's not obvious. I'll prove that on the next slide, but that basically concludes the proof once we prove this. Thus, there are infinitely many such numbers. In other words, this set here. So P, any prime that's not equal to 2 or 5 exactly divides an infinite number of these rep units. Okay, so let's now prove if we have P divides R sub K, that it divides R sub CK. Concerning the statement that I made at the end of the last slide, where I said since P divides R sub K, it also divides any rep unit whose length is a multiple of K. In other words, P divides R sub CK, where C is an integer. So let's see if we can prove that. By definition, R sub K is equal to this, and then R sub NK is equal to this expression here. So we'll let X equal 10 to the K, and then we can rewrite the numerator of R sub K as X minus 1, and the numerator of this term here, R sub NK, is X to the N minus 1. Then from algebra, we have this expression here, X to the N minus 1 equals X minus 1 times this sum here, and you can verify just by multiplying X times this, and then minus 1 times this, and most of the terms cancel. And we can write this as just X minus 1 times some integer I. We don't really care about what's in here other than it's an integer. So X to the N minus 1 is equal to X minus 1 times some integer. Then we substitute back in 10 to the X equals 10 to the K, and into here and here, and we get this. Then we divide both sides by 9, just to get it back in this form. And then we have that R sub NK equals I, some integer, times R sub K. So if P divides R sub K, then P divides R sub NK, which is what we wanted to show. Okay, so that was one version of the proof, and I have another version on the next slide, which I'll show you. On this slide, I have a second solution to our problem. This, I entitled it here Fermat's little theorem, but there's other aspects to it, but that's sort of the main part of the solution here. So we have two cases. If P is equal to 3, we know a number is divisible by 3 if the sum of its digits is divisible by 3. I proved that in the last lesson. R sub n consists of n1, so its digit sum is n. Therefore, R sub n is divisible by 3 whenever n is a multiple of 3. So R sub 3, R sub 6, R sub 9. So in the case of our prime P equals 3, we have an infinite number of solutions. Then the other case is when P does not equal 3. And recall from the statement of the problem, we were told P does not equal 2 and P does not equal 5. So P is relatively prime to 10. In other words, the GCD of P and 10 is equal to 1. We'll need that when we apply Fermat's little theorem down here. Also, since P is not equal to 3, P is coprime, in other words, relatively prime. I'm using these two terms here that mean the same thing, to 9. So the GCD of P and 9 is equal to 1. We start with the condition for divisibility. We'd like to know for what value of n this is true. and then we'll show a sequence of equivalences. So first, this is equivalent to this. I'm just plugging in the definition of R sub n here. And then if you multiply both sides by 9, you get this here, but you actually need to prove this. There's some catch to this, and I'll show you that on the next slide. But assuming that these two are equivalent, then you just bring the 1 over to the other side. And as we mentioned up here, P and 10 are relatively prime, so we can apply Fermat's little theorem, and that tells us that 10 to the p minus 1 is congruent to 1 mod p. So that gives us one solution, one value for n that'll work, so that we have divisibility of 9 into 10 to the nth power minus 1, which is equivalent to this, which is equivalent to this. And as I say, for the n set to p minus 1, we have a solution here. So what we want, though, is to prove there's an infinite number of solutions in this case. P doesn't equal 3. So for any positive integer k, raising both sides to the k power of this here, we get this. And if you recall from the previous lesson, I showed that if two numbers were congruent, then their powers, integer powers, are also congruent. So I'm applying that here. And of course, 1 to the k is 1. Thus, if we pick n equals k times p minus 1 for k greater than or equal to 1, we have p dividing r sub n. Hence, there are infinitely many n, all multiples of p minus 1, for which p divides r sub n. In order to complete the proof from the previous slide, we need to show that x divided by 9 is congruent to 0 mod p if and only if x is congruent to 0 mod p. In other words, effectively multiplying both sides of this by 9. If you recall on the previous slide, what we had, x was 10 to the n minus 1, so we're proving something a little more general here. And also, we're assuming that this is an integer here. X divided by 9 is an integer. So let's go in the forward direction. Let x equal 9t, where t is an integer, and that's goes to this assumption here. And then we have that p divides x divided by 9 from this here. But then x divided by 9 is t. So in other words, if p divides t, t is a multiple of p. So we'll say it's p times s, where s is an integer. And then we just plug this in for t here, and we get x equals 9ps. So in other words, p is a factor of x. P divides x, and that implies x is congruent to 0 mod p. So that's going in the forward direction. Going in the other direction, we assume this here, that x is congruent to 0 mod p, and we want to prove this. And we have 9 divides x from this here. So p divides x, and 9 divides x. Since p is prime and p is not equal to 3, p does not divide 9, so the GCD of p and 9 is equal to 1. Then from this here, from 9 dividing x, we can write x equals 9 times some integer k. And then from the other thing we have here, p divides x, that implies that p divides 9k. That's just plugging in this here. So by Euclid's lemma, which I proved several lessons back, but it's basically saying if a prime number divides a product, then it has to divide one of these. And we know that p doesn't divide 9, so it has to divide k. But k equals k, right from here, k equals x divided by 9. So p divides x divided by 9. In other words, x divided by 9 is congruent to 0 mod p. Okay, so that was quite a mouthful to prove something that seemed obvious, but you notice we had these little catches in here, different assumptions that we needed to make sure were valid in order to make this work in both directions. Okay, so let's proceed to the next problem. For our next problem, we have this. Prove that there are infinitely many primes of the form 6k minus 1. This is proof by contradiction, or at least the way I did it. And it uses a similar trick to what is normally used when proving that there's an infinite number of primes. So have a look at this, and I'll give you the solution on the next couple of slides. So as I noted, the approach I'm going to take here is proof by way of contradiction. So assume there are only finitely many primes of the form 6k minus 1. Let this finite set be S, P1, P2 up to Pn, and then consider the integer capital N equals 6 times the product of the elements in S minus 1. Note that N is an integer greater than 1. Since each of the elements in S is greater than or equal to 5, that's because of this condition here. The first, if you put in k equals 1, you get 5, and that's the first prime that would be in this set here. And n, and that's from this equation here, n is congruent to minus 1 mod 6, or equivalently, n is congruent to 5 mod 6. Since n is greater than 1, the fundamental theorem of arithmetic states that n must have a prime factorization. Let the prime factorization of n be q1, q2 up to q sub m. Since n is odd, right, anything of this form is odd because this is even, and you subtract 1 from it and you're going to get an odd number. So since n is odd, 2 is not a factor. Since n divided by 3 leaves a remainder of minus 1, again, looking at this here, if you divide this by 3, then it goes evenly into here, and then you have a remainder of minus 1. So that means 3 is not a divisor of n. Therefore, every prime factor of n must be greater than 3. Any prime q, in other words, from this set here, greater than 3 must be of the form 6k plus 1 or 6k minus 1. And 6k minus 1 is the same as 6k plus 5. If you start from k equals 0, you get the same numbers. So the idea is that a number, an integer, has to be of the form 6k, 6k plus 1, 6k plus 2, 6k plus 3, 6k plus 4, or 6k plus 5. That's the only 6 possibilities. And a number of those we can exclude in terms of not being prime, right? 6k could not be, anything of this form cannot be prime. It's divisible by 2 and 3 and 6. 6k plus 2 is divisible by 2, so that can't be prime. 6k plus 4, again, that's divisible by 2, so that can't be prime. And then even 6k plus 3 is divisible by 3. So we've excluded a number of the possibilities. For q, or any prime number greater than 3, it would have to be of the form 6k plus 1 or 6k plus 5, or equivalently 6k minus 1. So let's look into that a little further and see if we can find the contradiction. So if we take any two numbers of the form 6k plus 1, and we multiply them, so I've shown that here, we get this here, and then we can divide a 6 out of these first 3 terms. then we get something that's also of the form 6k plus 1. We don't care what this is, we just know it's an integer. If all prime factors of n were of the form 6k plus 1, then their product would also be of the form 6k plus 1. However, we constructed n to be of this form here, congruent to minus 1 mod 6, or in other words, the form 6k minus 1. Therefore, n must have at least one prime factor, let's call it q, of the form 6k minus 1. By our initial hypothesis, the set S contains all primes of the form 6k minus 1. Therefore, q must be one of the primes in our list p1, p2, up to p sub n. So this implies q divides the product, p, this we'll call it p, and now we have the situation q divides n, since it's a factor of n. In other words, it's one of the q sub 1, sub 2, and so forth. And q divides 6 times the product of the p's, since q is in this list from what we deduced up here. So if q divides both terms, it must divide any linear combination. We've seen that before. And in particular, it must divide the linear combination 1 times this minus 1 times n. And when you take this difference, you just get 1. So q is a prime number that divides 1, which is impossible. Thus, so we have a contradiction. Thus, the assumption that there are finitely many primes of the form 6k minus 1 has led to a contradiction. Therefore, there must be infinitely many primes of the form 6k minus 1. For our next problem, we have, suppose p is a prime number such that both p and p squared plus 2 are prime. Prove that p cubed plus 2 is also prime. Okay, I'll give you a hint. If you don't want to hear it, you might want to pause now. So the hint is there's only one value of p for which this works, but you need to prove that. So now I'll show you in the next slide how to do that. So let me point to this here. To prove that p cubed plus 2 is prime, given p and p squared plus 2 are primes, we must first determine the possible values of p. So that's the trick to this problem. By analyzing p modulo 3, we can show there is only one specific prime number that satisfies the initial conditions. Every integer p satisfies one of 3 congruences. Either it's congruent to 0 mod 3, 1 mod 3, or 2 mod 3. So let's look at the different cases. We'll look at p equals 3 first, and that's actually the only solution. Obviously, 3 is prime, we know that. Then 3 squared plus 2 is 11, that's prime. And 3 cubed is 27 plus 2, that's 29, so that's prime. So we have at least one solution. The problem is to show there isn't any other solution. So let's look at that. We assume p is a prime other than 3, so in other words, we're not in this case here. So it's not divisible by 3 in that case. Therefore, p is either congruent to 1 mod 3 or 2 mod 3, but not 0 mod 3 because it's not divisible by 3. In modular arithmetic, squaring 1 or 2 results in 1, at least mod 3, because if you square 1, of course, it's still congruent to 1 mod 3. And if you square 2, you get 4, but that's congruent to 1 mod 3 also. Thus, for any prime not equal to 3, we have p squared is congruent to 1 mod 3. Now we can add 2 to this, to look at our p squared plus 2, and we get 1 plus 2, or 3 mod 3. This implies that p squared plus 2 is divisible by 3. And since p is a prime greater than or equal to 2, not equal to 3, but it could be 2, the smallest value for p squared plus 2 is 6. Since p squared plus 2 is greater than 3 and divisible by 3, it must be composite. Thus, if p doesn't equal 3, the hypothesis p squared plus 2 is prime fails. And so we're just left with this one possible solution here. Okay, so that was the last problem in this lesson. I had initially planned on 3 lessons, but it's turning out this third lesson is getting quite long, so I'm going to stop here and publish this, and then the remainder of this lesson I'll make part 4 of my series on prime numbers.